So we're going to multiply this. Actually, let's do this down here. So we got 0.13 grams over 100 milliliters of water. So we're going to change the grams to moles using that. So 1 mole on top, 414 grams on the bottom. But now we got to change milliliters to liters because we want moles per liter.
Sorry for the interruption. We have the bug guy here. He's going to be coming around to all your classrooms to spray for not only the ants, but also if you have a wasp issue outside your window, if you could please give me a call so I can have him take a look at that for you as well. Thank you.
That was our wonderful secretary, Jessica Johnson, making a cameo appearance. By the way, if you have bugs in your house, deal with it. We can't send it over there to you. So now we got to change milliliters to liters because we want moles per liter as our label for concentration. So liters here, 1,000 milliliters here, 1 liter here. So we got here 0.13 divided by 100 divided by 414 times 1,000, and we get 3.14 times 10 to the negative third moles per liter, capital M. All right, so let's write the dissolving reaction for this copper to iodate. Solid, obviously very small solubility, so I think that technically defines itself as slightly soluble, but we still put the double arrow because it's not 100% soluble. Double arrow water is this copper 2 positive ions plus 2 iodate ions, so 2 IO3, charge -1, aqueous. And if you don't have a periodic chart that has IO3 or BRO3 or any of that stuff there, you can always use your powerful phone as a tool to find out. Just go to Google or Dogpile and ask for the the solubility or the charge rather of an ion, and it'll give it to you. And regardless, here we go. So that means the Ksp is equal to the concentration of copper 2 positive times the concentration of iodate, but because of the 2 here, this is going to put an exponent there. Okay? Now, again, let's suppose we have a chunk of this stuff, international symbol for chunk, lose x here, gain x here, and gain 2x here. So this becomes x times 2x, and because of the square here, we have to square it. You say, well, no, wait a minute, why are we doing that twice? Because mathematically that's how it works out. You have to do it. So when you put that all together, this gives you 4x cubed. Well, this is x. You have found x. So that the x is the solubility. How much dissolves in the water? So this is going to be 4 times, and then the value we got for that is 3.14 times 10 to the negative 3, and that is cubed. So 4 times, parentheses, 3.14 e negative 3 cubed. And we get 1.24 times 10 to the negative 7. So there's your Ksp value. So that's how they come up with all these values. They have to do an experiment or an analysis of the dissolving of a compound, which is very easily done. And then they go from there. Now, this is another Ksp problem, but now they give you the pH. Well, the reason why they give you the pH is because of this right here. So if we take a look at the dissolving of that, MgOH2 solid, double arrow, Mg2 positive, aqueous, plus 2 OH negative, aqueous. Okay? Now, pH means hydrogen, but we have OH, so that means we're going to have to change pH to POH. So it's 14 minus pH equals POH. So 14 minus 10.52 equals 3.48. So that means then that the concentration of hydrogen, or hydroxide rather, is 10 to the negative 3.48 power. And we calculate that nonsense out. 10 carat negative 3.48. We get 3.31 times 10 to the negative 4 moles per liter. Now, the Ksp expression then, again, we got a chunk of magnesium hydroxide, international symbol for chunk. Lose X here, gain X here, gain 2X here because of that 2 right there. So the Ksp for this is equal to the concentration of magnesium 2 positive times the concentration of OH negative, and because of that coefficient of 2, it's going to make that a square right there. And we know that this is going to be X times 2X quantity squared equals 4X cubed. So this is going to be 4 times 3.31 times 10 to the negative 4 quantity cubed. So 4 times parenthesis 3.31 E negative 4 quantity cubed. And we get 1.45 times 10 to the negative 10. Okay, so that's how we come up with Ksp. And we can use Ksp and work backwards and find out what the solubility is. So that's what the next problem is going to be about. So find the solubility of strontium carbonate. And when they say solubility, if they don't say otherwise, you can assume it to be moles per liter or capital M. So that really makes life a lot simpler. So let's do this one real quick. So we take the strontium carbonate, SrCO3, solid, double arrow with water, strontium 2 positive aqueous, plus carbonate 3 negative, or 2 negative aqueous. Okay, so the Ksp is 9.3 times 10 to the negative 10. So chunk, lose X, gain X, gain X. No coefficients, so we don't have to worry about that. So the Ksp is going to equal to concentration of strontium 2 positive times the concentration of carbonate 2 negative, and that's going to equal to X times X, which is X squared. And that equals the Ksp value, which is 9.3 times 10 to the negative 10. So now all we have to do is take the square root of both sides of this. So on the calculators, we get second square root, 9.3 EE negative 10. And we get 3.05 times 10 to the negative 5. Moles per liter. Last problem. Same kind of problem as that, only now we got we're going to have a coefficient in our dissolving reaction. Okay? So, here we go. PB, F2, solid, double arrow, wah-wah. Now, lead thinks it's a transition metal, has two charges, either positive 2 or positive 4. Since you know that fluorine is -1, times 2 is -2, that means lead is positive 2. So, this is going to be PB to positive aqueous plus 2F negative aqueous. Fluorine is diatomic as an atom, but not an ion. So you have to put the 2 in front. Okay? Okay. So we got a chunk of this stuff, international symbol for chunk, by the way. Minus X here, and 2X here. Okay? Okay? So, that means then that Ksp, which is the concentration of lead to positive, times the concentration of chloride squared, is equal to X times 2X quantity squared. And you gotta be careful that, man, people screw this up all the time. It's unbelievable. You have to spare not just the X, but also the 2. That's 4X squared times X. There's like 2 areas of screwing uppiness. That's a new word. And this gives us 4X cubed. And we want to solve for X, because X is the solubility, how much actually dissolves in water. So, set that equal to 2.7 times 10 to the -8. So we divide both sides by 4. X cubed is equal to 6.75 times 10 to the -9th. Double check if you want, but I'm right. And then you are to take the cube root of both sides. And I know the answer is going to be X equals something times 10 to the -3. And I know it's going to be 2 point something because it's between 2 and 8. So I'll just take the cube root of 6.75. Because I'm cocky as all get out. It might actually help if I used the cube root, which is math 4, and then 6.75. And I get, oh, that's right, because 8, see, that's what I get for being cocky. It's 2 is 8, 2 cubed is 8, so it's 1 point something. I'm a maroon. 1.89 times 10 to the -3 moles per liter. And there is the solubility, and there are the problems to help you get through the practice problems. Practice problems, I say? Why, yay, I say. I have practice problems for you. Let's take a look at them, shall we? They are, this is exciting. Page 795, those even number problems, the odd numbers that I did. You're going to have some fun, I know it. Better than those stinking titrations, don't you think? You'll see, it's not bad. Have fun.